We're going to be leading into graphing polynomials in our next video. So as a kind of a preamble to that, what we're going to do is we're going to learn what we call the leading coefficient test about a graph, okay? So when we talk about the leading coefficient test and when it comes to graphs, what we're trying to do is kind of catch what the end behavior of the graph is. And when we talk about the end behavior of graphs of polynomial functions, we kind of mean as x gets very large. So as x goes out to what we call positive infinity, we call this positive infinity here. And this is how you'd write it. As x approaches positive infinity, or as x approaches negative infinity, that would be saying as your x values you're plugging in get very, very small. What's happening to your y values, okay? So what's happening to your f of x values? So what we're going to do in this video is we're going to graph some pretty basic polynomial functions that contain only one term in them, so monomial functions. But we're going to change the degree and we're going to change the leading coefficient and talk about what that does to the end behavior of the graphs, okay? So you notice here that I say let's go graph f of x equals x cubed, x to the fourth, x to the fifth, x to the sixth. My question is, on the left hand and on the right hand side of our graphs, what's happening to our end behavior? So what I've got open right here is actually this. You notice that I have y equals x to the nth power up here, and right now I'm saying let's let n equal all these different things from 0 to 10 going up by 1. So when I say y equals x squared, what I want to do is I want to describe the end behavior of this graph. So the way we do it is this. What we're really going to say about all polynomial functions is as x gets very small, that is, as we go to the left of our graph, or as x gets very large, or we go to the right of our graph, our y values are either going to go up without bound. So in other words, our y values on the right side of this graph are continuously increasing. So we say y is going to positive infinity, and on the left side, as x is getting very small here, we would say that the left side, its y values are approaching positive infinity. The moment, though, I make this y equals x cubed, we'll notice that our end behavior changes. That is, as x gets very large, goes to the positive infinity on the right. As the x values we're plugging in get bigger and bigger, the y values we're plugging in are approaching positive infinity. Whereas as x gets very small, as x goes to negative infinity, or we go to the left, our y values are going to negative infinity. So what I want to do is I want to connect, is there a relationship between the degree of this polynomial, which right now is degree 3, and its end behavior? And what I notice is every time, let's just scroll through these, we say this is y equals x to the fourth, y equals x to the fifth, y equals x to the sixth, y equals x to the seventh, y equals x to the eighth, ninth, 10th. So I notice that every time our degree is even, what I want to point out is this. On the left side of my graph and the right side of my graph, the y values both went to positive infinity. They did the same thing, whereas when my degree was odd, the left and right hand side behaviors of my graph were different, okay? So for instance, when we say y equals x squared, we want to go write the end behavior of this. That was our goal here. We say, here's what this would look like. And so we say y equals x cubed. So we actually need to go back and say, what is y equals x cubed? What's its end behavior? And we said on the left side, our y values are decreasing without bound. So the way that we would write this statement is this. We would say, as x goes to negative infinity, our y values, our f values, are going to negative infinity. We can see that here. As x gets really small, our y values are going down. And then we say as x now increases to positive infinity, our y values were going to positive infinity. And we could complete these statements for all of these, but knowing how to write this is very important, okay? So we say, all right, well, what we figured out was this. When it comes to end behavior, on this graph we say as x goes left, y goes way down. As x goes to the right, y goes way up. We could have also written this end behavior thusly. And this is just kind of a nifty, quick way of doing it. But we say on the right side of our graph, our y values are going up, and on the left side our y values went down. So when we had y equals x to the fourth, how would we draw this? We saw that y equals x to the fourth was up, up. Whereas y equals x to the fifth was up over here and down over here, and then y equals x to the sixth, we said up and up again. So one thing I want to notice is this. In the leading coefficient test, if the degree is even, let's make a little note here, even, then what we see is the left hand side and the right hand side behaviors are the same. Okay, and if it's odd, the left hand and right hand side behaviors are different. Okay, so when we're making a graph, this is actually going to come in handy because right off the bat we can identify the degree of the polynomial and say, hey, look, anytime the degree is odd, it's going to be different behaviors, but every time it's even, it's going to be the same. We say odd, even, odd, even, odd, even. Okay, so now the only other thing I want to mess around with this is this. I wanted to graph these same four functions here, but you notice that I made the leading coefficient negative. And what this does to the graph, what does this do to my graph? So we'd say if I were to make this leading coefficient negative now, that is, go put a negative in front of this, we see that every time the degree is even, you can see it opens downward now. Every time the degree is even, it's still on the left-hand and right-hand side, the y values, go down and go down. If it's fourth degree, as x goes to the left, our y values go negative infinity. As our go to the right here with our x values, our y values also go negative infinity. So whenever the degree is even, we still have left and right hand behaviors of the graph that are the same, and whenever the degree is odd, we say whatever it does on the left side, if it goes up, then the right side would be opposite. So this still holds true, but what I want you to notice is, now what holds true amongst all the graphs? On the right side of the graph, you'll notice that it always ends downward on the right side of the graph. So what we're seeing here is that when our leading coefficient is negative, the right-hand side of the behavior is down, and when the leading coefficient is positive, the right-hand side of the behavior is up. You'll notice that all of these graphs up here had something in common. They all ended up on the right. So when we put these in now, we say, okay, when I have negative leading coefficients, let's sketch in our diagrams here. We said negative x cubed, we had something that ended down on the right, and because the degree was odd, started up on the left. Whereas when I have something like this, we say this negative leading coefficient means I end down on the right, but also that I started down on the left because, I had an even degree. So same thing throughout all of these. We say negative leading coefficient means how I end on the right, and then odd degree would mean I started differently. And then we say negative leading coefficient here means on the right side I end downward. But on the left side, since I have an even degree, I must have started the same way. So all of our functions, what I can tell you about polynomials is they do whatever they want. They may look like this, but we can at least determine, from something like what we've explored right here, that this had to have an even degree if I just made this up. And we could also say the leading coefficient is negative, and only because the right side of this graph ended downward. So we say the degree, this is important. These two things hold true. And then we also talk about the leading coefficient. So let's write these things in. The leading coefficient. We say if it's positive, then what we get is something like this. The right-hand side y values approach positive infinity. So that means on the right side of our graph, let me try to squeeze this in here. On the right side of our graph, it goes up. So it could be like question here, 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 but we say it's up on the right side, and we say negative. Leading coefficient means that on the right side of our graph, it ends downward. It may start up or start down on the left, but it ends downward, okay? So using what we know now, in the next video when we say go graph something like this, 2x to the third power plus 4x squared minus 5, what we can already say is that our degree here is third degree, so it is odd. So we have different left and right hand side behaviors, so different behaviors on the left and the right hand side. And then we say the leading coefficient in this case is positive. So I know that it ends up on the right. So if I had to describe the behavior of this graph, it ends up over here, and since it had an odd degree, it must have started down here. So we're going to get a graph that does maybe something like this. But we have an inclination of its end behavior just by looking at the degree and leading coefficient. So make sure you have these generalizations down so you can determine end behavior.